So now we're going to talk about the division algorithm, commonly referred to as long division. And as we mentioned in our discussions of the previous algorithms, the last thing we want to do as a teacher is just give our students a list of steps to carry out without any understanding behind those steps. Think about how difficult that would be in the long division process. There's a lot going on in long division. So if you were demonstrating 747 divided by 3 to your students, and you told them a list of steps, there are a lot of steps for them to remember. First, they have to divide 7 by 3, then they have to multiply 2 times 3, then they have to subtract 7 and 6, and then they have to repeat the process. So all of these steps are seemingly different than one another. In one step we're dividing, in another step we're multiplying, in another step we're subtracting, and then we're continuing. So again, just learning the long division process with a step-by-step procedure with no understanding is going to lead to misunderstanding and a non-complete understanding of what's going on. Okay? So like we did with addition and subtraction algorithms, we want to motivate all of the steps in the procedure. So we want to have an explanation for everything we write down in the algorithm. There needs to be an answer to why we do that. Now, in the addition and subtraction and multiplication algorithms, to a certain extent, we use chip models primarily to motivate the steps in the algorithm. Now, there is a version of a chip model for division. I'm going to attach a page from the Singapore math book to a PowerPoint that will link up to this discussion because it's quite a cumbersome model. And in many cases, we don't really want to go through the entire model to illustrate division. It can be a little more, perhaps more beneficial to introduce the steps of the long division process in the context of a word problem because kids can associate the step-by-step solution to a real-world problem with the necessary steps that are involved in the long division process. Okay? So we might start with the following word problem to illustrate 747 divided by 3. 3 friends win $747 in the lottery. If they split the money evenly, how much money will each person receive? And first and foremost, our kids should recognize that the solution to this problem, or this problem represents partitive division for 747 divided by 3. And that's the first part of this process. The kids need to know that the solution of this problem is the solution to the problem 747 divided by 3. Now again, what we want to illustrate in this explanation is not necessarily the answer to the question, it's instead what are the steps involved in solving this question. And for that reason, we need to take a little bit of a departure from how this would work in the real world. In the real world, if you went to a bank and asked for $747, odds are you would get 7 $100 bills, a couple of $20 bills, a $5 bill, and 2 $1 bills. But that's not really going to help us in this context because remember, we're trying to explain the long division process. And the long division process is based on place value. And place value, there's no place value for 5s or 20s. There are place values for 1s, 10s, and 100s. So for that reason, we are going to consider the $747 being split up into 7 $100 bills, 4 $10 bills, and 7 $1 bills so that the method, or that our solution process kind of corresponds and connects with place value concepts. And hopefully, as a teacher, you can easily imagine doing something like this with, for example, Monopoly money. Okay? So what we're going to do is we're going to just think about how would we physically solve this problem. Let's say we had 3 friends sitting at a table and we had $747 with these denominations, 7 $100 bills, 4 10s, and 7 1s on the table. We also have the ability to make change. We have a banker. And the question is, how would we physically solve this problem? And what we're going to do is we're going to translate all of the steps of solving this problem to the algorithm. So the steps that we're going to carry out in the physical solution of this problem are going to be translated to the algorithm. And in this way, hopefully the students will be able to make a connection between the seemingly disparate steps that they take to solve this problem on the algorithm. They'll be able to connect it to something that makes sense to them. Okay? One way of thinking about this long division process is that we ask and answer a series of questions at each stage. And these questions would correspond exactly to how we would solve this problem in the real world. So for example, how would we start this process? We have $747 on the table, we have 3 people, we need to divvy up this money evenly. We would start by taking those hundreds and splitting them up evenly. So really what's happening is we have 7 $100 bills that we want to split evenly 3 ways. Well, what arithmetic is that? That's the arithmetic 7 divided by 3. So the first question that we would ask is how many hundreds would each person receive? And the answer to that question is the total number of hundreds that we have, in this case 7, divided by the number of people that are there, in this case 3. So 7 divided by 3 is the first thing that we would need to do to solve this problem. 7 divided by 3 is 2. So that's why, in the context of this problem, each person is going to get $200 bills, and that's why the partial answer to this problem is a 2 in the hundreds place. So that's why, again, remember, the answer, the point of this process is to explain why we do everything we do. That's why we put a 2 in the hundreds column of the answer. It's because that's the answer to 7 divided by 3. We're divvying up the 7s first. Okay, so now imagine the table that we're sitting at. 6 hundreds have been removed from that table, right? Because all of us got 2 hundreds. So that's another question that we would ask and answer is how many hundreds were distributed? How many hundreds were given out? Well, if each of 3 people were given 2 $100 bills, then the arithmetic that's needed to solve that problem is 3 times 2. So that's why, again, remember we're answering this question why at every stage, that's why the next stage of the algorithm we multiply 2 by 3, because we have to figure out how many hundreds were distributed. In this case, that's why we multiply 2 times 3 to obtain 6. So that's the second question that we would ask at each stage. How many, in this case, hundreds were distributed? That's why it's 2 times 3. Okay, well the next thing we need to do is figure out how many hundreds are left over. Well, if we started with 7 and we gave away 6, then the way we would figure out how many are left over is we would just subtract 6 from 7. So again, that's why at this next stage in the algorithm, we subtract 6 from 7. So kind of the first stage of the division algorithm is complete. We have successfully divvied up the hundreds. Each person got 2 hundreds, there's 100 left over. Now, in the context of sitting around a table and doing this, this would take about 5 seconds, but what we really want to do is think about how those steps, sitting around the table divvying up the hundreds, correspond to what we need to do on the algorithm. And what we need to do on the algorithm, there's actually 3 things that we need to do on the algorithm, right? We have to first divide 7 by 3 to figure out how many hundreds each person gets. We then need to multiply 2 by 3 to figure out how many hundreds were given away. And then finally, we need to subtract 6 from 7 to figure out how many hundreds are left over. Okay? That's the first stage of the algorithm. But again, you're not done, right? Because you still have one $100 bill on the table, those original 4 10s, and those 7 1s. So now you have to figure out what are you going to do with that one $100 bill. There's 3 of you sitting around the table, and there's only 1 physical bill to divvy up. Well, this is where we need the banker, because the banker is going to make change for us. So at this stage, we are going to change out the remaining hundreds. In this case, there's 1 remaining 100. We're going to change that remaining 100 out for 10 10s. Okay? So oftentimes when this algorithm is taught, some strange things happen at this point in the algorithm. Arrows are drawn or funny things happen to get this 4 down here. But really what's happening is that it's the number of 10s that we have now, right? 4 was the original number of 10s we had, but with this 100 that was left over, we end up making change and changing this 100 into 10 10s. Now, how it's organized on the algorithm is that these 10 10s add to these original 4 10s to obtain 14 10s. It looks like this 4 is just kind of naturally coming down here, but really what's happening is it's being added to the 10 10s that we obtained by changing 100 into 10 10s. And now, we just repeat the process over again. So all of those questions that we asked at the first stage, how many hundreds did each person get? How many hundreds were distributed? How many hundreds are left over? Those exact same questions are going to be asked now. It's just the word hundreds is going to be replaced by tens. There are 14 $10 bills sitting on the table. We have 3 people. We need to divvy them up equally. So that entails dividing 14 by 3 to see how many $10 bills each person is going to get. 14 divided by 3 is 4. So each person is going to receive 4 $10 bills. We now need to know how many $10 bills were distributed. Well, if each of 3 people received 4 $10 bills, then 4 times 3, or 12 $10 bills were given away. And we finally need to see how many $10 bills we have left over. Well, if we started with 14 and we gave away 12, then we subtract 12 from 14 to find that there are 2 $10 bills left over. So you'll notice, at every stage, every number that we have written down and every operation that we have done, there's a reason why we did it. And the reason is based on simply solving this problem that we started with. Okay? Finally, again, we see that we are going to need to make change. There are 3 of us around the table. However, there are only 2 $10 bills. So what we need to do is make change again. We're going to take all of these remaining 2 $10 bills and change them into ones. So since there are 2 10s, that corresponds to 20 ones. Again, sometimes it magically looks like this 7 just kind of floats down here. That's really not what's happening. What's happening is we started with 7 ones. The 2 10s that we are left with from the last stage of the process get converted into 21s. We add 20 to 7, that's where the 27 ones comes from. So we have one more stage in the algorithm, we have to divvy up these ones. There are 27 ones, there are 3 people, we divide 27 by 3 to see that each person gets 9 ones. We multiply 3 by 9 to see how many ones were given away. 3 times 9 is 27. And to see how many ones are left over, we subtract, in this case, 27 from 27 to get 0. So the important part of this process, again, is not seeing that the answer to 747 divided by 3 is 249. Okay, the important part of this process is that this is a very complicated procedure. There's a lot of things going on. And motivating the algorithm in this way, starting with a word problem that students can understand is going to be a division problem, and then simply solving that problem and taking the steps of your kind of real-world solution, translating them to the steps of the algorithm, gives kids something that they can attach to. So they're not just carrying out an arbitrary sequence of steps that has no meaning to them. So now there's some meaning, and hopefully they'll be able to remember the algorithm more accurately.